Some clouds can weigh thousands of tons. How can something so heavy float across the sky? Well, today I'm going to introduce aerosol particle motion and how particle drag affects cloud droplets. In your physics class, you may have been taught Newton's laws of motion. These laws are explained by the constant acceleration relationships given by the Suvat equations. If I throw a ball with initial velocity u0, with the only acceleration being gravity, we can calculate the trajectory of the ball, the time of flight, and the final velocity. But if you throw a ping pong ball with the same initial velocity, you'll notice it doesn't follow the same parabolic path. That's because Suvat doesn't take into account drag forces. What is drag? Drag is the bombardment of the ball with air molecules which provide resistance to its movement, causing deacceleration. When looking at aerosol particles, we use Stokes drag to describe this. This is the Stokes drag equation. It relates the drag force to three different variables. The viscosity of air, which describes how thick the fluid is. For example, honey is more viscous than water. Velocity, how fast the particle is travelling, and the particle radius. If we consider a spherical particle falling through the air, what are the forces acting on it? Gravity accelerating the particle downward and Stokes drag acting upward, which resists this acceleration. When the particle reaches a terminal velocity, which is no time at all for an aerosol, these two forces act equal and opposite to one another, meaning there is no further acceleration of the particle. If we equate the drag and gravitational force, we can rearrange the equation to determine an expression for terminal velocity, and we see that terminal velocity is proportional to the radius squared. What does this mean for falling aerosol particles? As you can see from this model, the smaller particles fall much slower than larger particles. But how does this relate to clouds not falling out of the sky? Clouds are formed from millions of tiny aerosol droplets. These are 30 million times smaller than a ping pong ball. The very small droplets in clouds are falling, however the terminal velocity is small because the radius is so small. For instance, a water droplet with 10 nanometer radius would take 2.6 years to fall 1 meter. You may be wondering, if it takes that long for a droplet to fall, why does it rain so much in the UK? These tiny droplets that exist in the cloud combine with one another over time into larger droplets. This is known as coalescence. This simulation represents the movement of particles in a cloud. The simulation starts as lots of small particles. If you follow one particle, you'll notice it increases in size over time when it collides with other particles. The result is a smaller number of large particles. This increase in particle radius increases the terminal velocity, and the droplets fall with significant speed as rain. Aerosol science is truly interdisciplinary, and aerosol scientists have to use Stokes drag to understand particle movement in many different real-world challenges. In the top left-hand corner, we have a video of how different aerosols move around the world, such as Saharan dust clouds and weather systems. In the top right, we can simulate how aerosolized viruses can move around a room and how ventilation can mitigate spreading. In the bottom left, we have an aerosol sampling instrument, which selects particles based on the effects of drag. This allows us to classify particles of certain diameters. In the bottom right, we can use particle drag to determine where an aerosol will deposit after it has been inhaled, useful for designing inhalers and drug delivery systems. Follow the links to find out more.